Well, hi, guys. Good morning.
What? Oh, hey. Hi, guys.
Mr. Kane.
Good morning, ladies and gentlemen.
You can't change the routine, Mr. Kane. You can't.
All right, so should we start over or should we just keep going?
Nah, just keep going.
Keep going. Okay.
I woke you up.
All right, limiting and percent yield. All right. So we are beginning the limiting reactants and percent yields part of the chapter.
Which we actually touched on briefly on that last one when we were talking about the cheese and the bread.
The cheese sandwiches. You mean they actually had something to do with chemistry?
Yes.
I guess we did some stoichiometry problems with them.
Yeah. Well, I love food analogies, so what the heck.
All right, so different terms that you need to know. Limiting reactant. So the limiting reactant is the reactant that limits the amount of product that's formed. So it's the thing that you don't have quite enough of.
Okay.
In that example that we were doing the other day, I believe that it was the bread that we didn't have enough of. We only had 7 slices of bread and 6 slices of cheese.
Yeah, the bread kind of limited how many sandwiches we could make. Because,
Right.
you're right. We had one leftover piece of bread.
The excess reactant is the reactant that does not limit the amount of production. Okay, so that's the one that we got plenty of. That was the cheese.
I think I said that wrong, too. We had a lot of cheese left over, didn't we?
You had a lot of cheese
left over. That was the
left over,
excess.
yeah.
The bread limited us.
Mm-hmm.
Okay.
Theoretical yield is the maximum amount of product possible given the limiting reactants. Remember we said we could make 3 cheese sandwiches from 7 slices of bread and 6 pieces of cheese?
Yes.
That's because we only in theory could have made 6.
So the theoretical yield, you know what I call the theoretical yield? That is the amount in grams that you calculate with paper and pencil.
Okay.
That is what you should get if you did a perfect lab.
If you did it perfectly, yeah.
And of course, nobody ever does a perfect lab. So.
Yeah, but you can always get within a certain percentage.
Yeah.
Mm-hmm. The actual yield is if we were actually to go in lab, which we'll actually do a lab like this.
Yeah.
And produce a certain amount of product, and that's going to be the actual amount. After you take away the fact that some of it's spilled, or you didn't quite measure properly,
overcooked it, walked away from it, talking about your homecoming dress, blah 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 blah.
Yeah, homecoming's well over. No one's going to be doing that.
Whatever it is. So theoretical yield is the calculated one. Actual is the experimental.
Mm-hmm.
Okay.
What you actually get in lab.
All right.
That's why it's called actually get. All right, so and then the percent yield, you're going to want to see how far off you are.
Rarely get 100%, isn't that correct? Rarely.
Right, you're looking at wanting to get somewhere between 85 and 100%.
Right.
Probably, yeah, because 10 to 15% in the chemistry lab isn't too terribly bad. Okay, and there's the equation for it.
So actual over theoretical, actual is your experimental, it'll always be a smaller number. Theoretical is the one you calculate, and it'll always be the exact number. It'll always be the larger number, because your actual is going to be a smaller amount.
Hopefully, yeah.
Well, yeah.
As long as you didn't do something really... Okay. So solving theoretical yield problems. It's kind of like those, you perform stoichiometry problem on each reactant to form mass, unless you're told otherwise, right?
What do you mean each? You mean there'll be 2
stoichiometry problems? All right, so in solving theoretical yield problems, the basic idea is that you're going to perform a stoichiometry problem on each reactant to form mass of the same product.
Okay.
All right, unless you're told otherwise. All right, so in solving theoretical yield problems, you perform a stoichiometry problem on each reactant to form the mass, unless you're told otherwise at the same.
Okay, but if it's a limiting excess problem, they're actually going to give you the quantity of 2 reactants.
So you label the smaller amount of product as the theoretical yield, the smaller mass. So when you get to the end, the least amount is our theoretical yield. Kind of like with the cheese sandwiches.
Okay.
Label the reactants that gave you the theoretical yield as the limiting reactant. That's when you don't have enough of.
So number 2, when you compare your 2 answers of the amount of product, you pick the smaller one, and that's your theoretical yield. Then you follow that back and circle your reactant that gave you that small amount. Is that what you're saying?
Correct. Label that circle as the limiting reactant. All right, here's our sample problem. Determining the limiting reactant and percent yield for the following. Okay. So we're given, it's the Haber process again. 14 grams of nitrogen react with 3.15 grams of hydrogen to give an actual yield of 14.5 grams of ammonia.
Okay, hold it. I don't get it.
All right, well,
How do we get the 14.5 grams? Is this done for us already?
This lab was done for us already. They told us that the actual yield was 14.5. That's what they actually got.
So this is an experimental that value. Okay.
This is an experiment that was done for us. So they said they started with exactly 14 grams of nitrogen and 3.5 grams of hydrogen.
So since they gave us the quantity of both reactants, we have to do a limiting excess problem. We have to do stoichiometry twice.
Right. We have to do it for nitrogen and for hydrogen so that we can see which one will make less ammonia.
Okay.
Okay.
They gave it to us in mass.
Yep, they gave it to us in mass, which means we're going to have to do a longer stoichiometry problem here.
All right.
So we start out with 14.0 grams of nitrogen.
Better write small, Mr. Kane. So since the balanced chemical equation is in language of moles, that 14 grams isn't the same language, so we do have to convert.
All right, so 1 mole is 28.02 grams of nitrogen. A mole of nitrogen is going to give me, well, this is the stoichiometric ratio. I want to convert to another substance, in this case, ammonia.
This is the stoic part, right?
Yep, so moles of ammonia. So according to the balanced chemical reaction, 1 mole of nitrogen gives me 2 moles of ammonia. So my grams of nitrogen and my moles of nitrogen are now canceled. And according to the instructions, I want to go from moles of NH3 to grams of NH3.
Which would be molar mass, because you want to just convert to mass. And
so
that's 17.04? 17.0 grams of product?
17.0 grams of NH3. Okay, that's one stoichiometry problem done.
All right, so we know that if we had 14 grams of nitrogen, we theoretically make 17 grams of ammonia.
Right, but that's not our theoretical yield because we have to find out first.
That would be assuming we had excess hydrogen, correct?
Right.
All right, so now we're going to do a second stoic problem, assuming we have excess nitrogen, and then compare the two.
Right, we don't have excess hydrogen, so we're going to have to do the hydrogen problem. So 1 mole is 2.02 grams.
Wait, why isn't it 3 moles? I see a 3 in the balanced chemical equation.
Because that's not the molar mass, Mrs. G.
Okay.
So the molar mass says that 1 mole is 2.02 grams. If you wanted me, I could put 3 moles on top, but then I'd have to put 6.06 grams of hydrogen.
I don't want to mess up that nice definition. The mass of 1 mole is 2.02 grams.
Right. So a moles of hydrogen, and I'm going to turn this into moles of ammonia. So looking at my balanced equation, 3 moles of hydrogen give me 2 moles of ammonia.
Right.
So moles of hydrogen cancel.
And theoretical yield is usually in mass. So one last ratio. And the last ratio looks the same for both of them, doesn't it?
Yeah, I guess it does, because it's the molar mass of ammonia. So 1 mole is 17.04 grams.
Which is 17.7, I hope. Let's check my work.
Okay.
You keep writing.
All right, so we've just found out that if we had 13.15 grams of hydrogen, it would be capable of making 17.7 grams of ammonia, assuming that we had excess nitrogen.
Or at least enough nitrogen, but we don't.
Now, we only have 14 grams of nitrogen, 3.15 grams of hydrogen, so we can only make the smallest amount of ammonia that's given here. So this number here
is the smallest amount.
So
that's our theoretical
yield. So this
yield.
is my theoretical yield, so I'll label it. Do you let students abbreviate?
Sure. Oh, God, yes.
CY, theoretical yield.
Okay, thank you.
Okay.
I made it funny.
Yes, you did. Thank you. Thank you. I see what you did there. All right. So that means that this here, 14.0 grams of nitrogen, would be my limiting reactant.
Okay. And the hydrogen gas, there'd be leftover hydrogen gas because it's the excess one,
right.
Yeah?
This is the one that I've got excess of. So this would be my excess reactant.
So when you're going mass to mass in a theoretical stoichiometry problem, you are going to be faced with 2 stoichiometry problems, and each of them containing 3 ratios, huh?
Yep.
And only one of those ratios is the actual stoichiometry, correct?
Correct.
And that's that middle one. The other 2 are just converting from mass to moles, and then moles to mass.
Mm-hmm.
Okay.
All right. Now we've got one more thing to do. They asked us to find the limiting reactant, which we now have done.
Okay.
But they also asked us for the percentage yield.
I see the actual yield. That's what was given in the problem. That's that 14.5 grams
right.
of ammonia. That's the experimental. And usually theoretical experimental is in mass.
Mm-hmm. So we put the experimental yield, the actual yield on top, 14.5 grams. We divide that by what should have been the total, 17.0 grams.
Theoretical. Yeah,
okay,
actual over theoretical.
So this is the part that we got, the 14.5. This is the theoretical whole. We multiply by 100, and we should get a percentage, 85.3% yield.
So what that tells you is you got approximately 85% of your ammonia.
Right. Means 15% of it leaked away. All right. Determining limiting reactant theoretical yield and percent yield if 14 grams of ammonia are mixed with 9 grams of hydrogen and 16.1 grams of ammonia form.
Okay, so this is the Haber process again. There are different quantities.
Yep. Hey, we started with 14 grams of nitrogen again. Can I just copy that from my last problem?
No, Mr. Kane. Do the work all over again. Comes out to be 17.0, which of course is what we got last.
Okay. Okay, and so for the interesting part of the problem, now we have
only 9 grams of hydrogen gas.
Only 9 grams of hydrogen gas, which is actually...
Well, if that's a smaller number, aren't we going to have that being the limiting reactant?
Moles of hydrogen.
So molar mass.
Molar mass. 1 mole of hydrogen is 2.02 grams.
It's a diatomic. Back to the balanced chemical equation, the mole-to-mole ratio from hydrogen to ammonia, and that's the coefficients. Ripped right out of the balanced chemical equation. And then the last ratio is exactly the same.
You can do moles of NH3 on the bottom and grams of NH3 on the top.
6? What? That's a lot, Mr. Kane.
Uh-huh, that is a lot, but that's just because we got a lot of hydrogen.
I'm going to just check my math for a moment.
The theoretical yield is still only 17.0 grams of ammonia.
That's the smaller amount, so
right.
It's still nitrogen gas being the limiting reactant.
This is still my limiting reactant for my nitrogen gas, which means that I have an excess of hydrogen. That's my excess reactant.
All right.
And then let me erase a little bit of this so I can show my percent work.
So once we're done with the excess guy, we don't really look at him again, do we?
Not
He's
really.
kind of out of our life.
And he needs to be there so that you can grade it. But
yeah, okay.
Let's see. According to this, we formed 16.1 grams of NH3.
Which is the actual or experimental.
We divide that by 17.0 grams, multiply by 100.
94.7%. Ooh, that's a better percent yield
That's a better
than the other
percent
one.
yield than last time.
I'd do this experiment. These quantities. That's awesome.
Yeah, but you're going to feed the world.
Yeah,
or
that's
blow
a lot.
It, or blow it up.
Blow it up, yep. Fertilizer, whatever.
94.7. All right. What's that I smell?
Fertilizer?
It's homework
geez.
number 2.
More homework.
Okay. Oh, hey.
Oh, I could do this one.
Bring your notes and questions to class.
Hey, I can do this homework.